Right. In the last section of this chapter, which we are going to consider the digital logic as a complete problems and how are we going to solve those problems, because we have got the knowledge of gates, the Boolean expressions that we can represent the gates and the functions. Now, if we have got a problem description, how are we going to approach those problems in order to solve them? So, logic problem solving, we have got the word description generally. We have to translate to a truth table, to a meaningful binary patterns. And then from those patterns, we can derive the expressions like minterms and the maxterms that we have done. And then we can apply algebraic manipulation and simplify it. So minimal sum of product form, two-level LDOR get networks. Minimum number of terms means minimum number of AND gates, minimum number of literals input to the AND gates. Product of sum forms, number of factors like number of OR gates and so on. These can be all simplified so that we can have an expression or an implementation that we can derive the circuitry for it. Okay, let's see the first example. It says, I can recommend flight seats to a couple if there are two or more adjacent empty chairs out of three in a row. So we are actually looking at two or more chairs next to each other, which are empty. So let's say we have got three seats, A, B, C, okay? And we are actually looking for two adjacent chairs, so either A and B or B and C. They have to be free so that we can book it, arrange it for couple. Okay, so if we put into a truth table, and we also have function f as an output, so three variables, 8 possible combinations. And these 8 possible combinations can be outputted based on the problem description. So we are looking for adjacent empty seats. So adjacent empty seats, we can say 0 for empty and 1 for full or occupied. Okay. And in this case, if we have got three empty seats, let's start with the first one. Three empty seats, either A, B, or B, C. We can arrange it or fill it with our couple. So we can say this is one. A and B's are empty. That means that's also one. A and C are empty. As there is someone in between these couples, we cannot book it for them. B, C are full. A is empty, so we cannot book it. B and C is empty, so we can book it. And then B is empty, we cannot book it. C is empty, no. And all of them are occupied, so we cannot book it. So now we have got an expression so that this is minterm 0, this is minterm 1, and this is minterm 4 that we can actually have as a expression. And I can say that f is equals sum of the minterms 0, 1, and 4. And in this case, I can say f is a prime, b prime, c prime, or a prime, b prime, c, or a, b prime, c prime. And if you want, you can also write the max terms for the canonical standards product form. So this is going to be 2, 3, 5, 6, and 7. And we can write those products as well. So in the end, this is how we can end up with an expression, and we can easily implement this expression using logic gates as we have seen, and or an inverter gates. Then another example that we can have draw a number between 0 and 15 and ring the bell f equals 1 if the number is greater than or equal to 14. Now, if we are having 0 to 15, that means 0 to 15 is 16 possibilities. And if we are looking at something greater than or equal to 14, it's actually 14 and 15 are only going to be output 1. Okay, so truth table needs 4 bits because 0 to 15 can only be represented with 4 bits. And then the last two, 1, 1, 1, 0, which is 14, and 1, 1, 1, which is 15, are going to be ones as they are greater than or equal to 14. So we can easily write an expression A, B, C, D prime, and A, B, C, D. Okay, and we can simplify it, and you can get ABC as a simplified expression. Now, example 3, it says you are to design a number analyzer which has one 3-bit unsigned integer. Okay, so we are going to get 3 bits out of it. I'll say ABC again. And or you can say N0, N1, N2. It's up to you. I'll say ABC. It's easier to follow it. And we have got 5 outputs over there, which we have got small, large, odd, non-zero, even non-zero, and prime. So 3 inputs, 8 possibilities once again that we need to include into our design. Oops, 1, 1, 0, 1, 1, 1. And we have got some conditions over there, which is given in the table that we need to fulfill based on the expressions or the combinations we will have. So small, large, odd, even, and prime. Let's start with small. So small is a number which is less than 3. So number which is less than 3. So 0, 1, 2, and less than or equal to 3 means these are all going to be included, and the other ones are going to be zeros. And for the large one, we need to have a number which is greater than 3. Now, if we have got a number greater than 3, that means it's going to be like the opposite of the small one. So for having an opposite of the small one, that means these are going to be zeros. Anything greater than 3 are going to be ones. And odd means an odd non-zero. Sorry, odd. N is an odd number and it has to be non-zero. That means odd number, 1 is odd, 2 is not, 3 is odd, 4 is even, 5 is odd, 6 is even, and 7 is odd. And even non-zero means 0 is also 0, 1 is 0 because it's odd, 2 is 1, 3 is odd, 4 is 1, 5 is odd, 6 is 1, and 7 is odd. So this is even. And the prime numbers are 2, 3, 5, 7. So 2, 3, 5, and 7 are ones, and the rest are going to be zeros. So we have outputs for each of these small, large, odd, even, and primes, and we can easily derive an expression for them. So, or the min terms for it. So S is the sum of the min terms, which is 0, 1, 2, 3. And L has got the sum of the min terms 4, 5, 6, and 7. Odd has got the min terms 1, 3, 5, and 7. Even has got the min terms 2, 4, 6, and the prime has got the midterms 2, 3, 5, and 7. So when you look at these expressions, we can derive the expressions for them as well. For S, like small, large, odds, and primes, if you can factor out the common variables like x prime plus x, we are always going to get 1 from it to reduce it. And for the even, we just have 2, 4, 6, and I'll just do even, but you can do the other ones as well if you want, where we have got 2 is A prime, B, C prime, or 4 is A, B prime, C prime, or 6 is A, B, C prime. Now, can we simplify this? When we look at it, we have got what we have in common over here is C prime A, C prime. We can take that out. A prime, B, C prime, or A, C prime is out, B prime plus B. This has gone, and we have got A prime, B, C prime, or A, C prime. Where C prime is common, we can take C prime out, A prime, B, or A in this case, and then multiply them out. So C prime, A prime plus A, and A plus B is what we are going to get. This is 1. This is going to be C prime, A plus B. And that will be the, or you can write it as A, C prime, or B, C prime. So you can find the other ones using the similar method by using algebraic manipulation and implement them. Okay, the next thing that we want to talk about, we have got these logic gates and or not that we have seen in the chapter 1. In addition to that, by using that gates, we can actually create some other gates from it, okay? Like X but not Y, like Y but not X, exclusive or, NOR functions, and so on. So if we start again with the AND function, now AND function, when we have X, Y, and F, we have got 0, 0, 0, 1, 1, 0, 1, 1, and 0, 0, 0. When both are 1, output is 1, and we say that it is X dot Y is equals F. Now, AND function is like X, Y, and F, okay? Now, what we can do is, if we add an inverter in front of it, okay, so this is like, I'll draw the symbol first. This becomes a new gate, which we call it not AND or NAND. And in this case, it's just the opposite of AND. So 0, 1, 1, 0, 1, 1. Opposite of it, that means zeros are becoming ones and 1 becomes 0. Okay? And the expression for it is F is equals X dot Y, parentheses, the prime. So we are taking the inverse or the not of AND. I actually call it NAND. And the same applies for OR, where we have got X, Y, and F, 0, 0, 0, 1, 1, 0, 1, 1, and 0, 1, 1, 1. And the implementation is like this, X, Y, and F. Okay, so f is equals x plus y. Again, if we introduce a inverter in front of it, which becomes like a something like this, they are both the same thing. Now this becomes not or nor, we call it. X, Y, and F, 0, 0, 0, 1, 1, 0, 1, 1. And it's opposite of OR. So when it is 0, it's going to be 1. And when it is 1, it's going to be 0. Okay? So it is like F is equals X plus Y prime, inverted. You know inverter now. We have seen inverter. But we can also have inverter bubbled. So inverter is actually going to give you a buffer without a bubble. So normally inverter is giving you f as a prime. And this one is just f is equals a. It's like a wire. So you're just holding the previous value over there. Okay. And once again, from the table, AND, OR, and inverter functions, the truth tables, algebraic functions, you have to learn these. Without knowing these, you cannot succeed with any other chapters. So you have to learn these, their symbols, their algebraic expressions, and their truth tables. And the buffer, F, is following X. Whatever we have got on input, it will be an output. NAND function is a inverted version of AND, and NOR function is an inverted version of OR. Another two important ones are XOR. So exclusive OR function, it's also known as odd function. Okay, so if we have got odd number of ones, output is 1. So let's say A, B, and F, 0, 0, 0, 1, 1, 0, 1, 1. Now, if the number of inputs, if the number of ones are odd, then the output is 1. Now, both are 0, it's even. Only one of them is 1, it's odd, odd, and even. So this is the expression that we have got. You can either call it as A prime B or A B prime, or you can use a special symbol for exclusive OR, which is add operation plus inside of a circle A XOR B. Okay, and the symbol for it, it's like an OR, but there's another line in front of it, which we are using it. And this is odd function, which is exclusive OR. Exclusive NOR is another one, which we call it even function. So we are looking for even number of ones, or equivalence function that we call it. When both inputs are equivalent, that means output is going to be 1. So 0, 0, 0, 1, 1, 0, 1, 1. Now both inputs are equal. 0, 0, it's actually an even function, so it's 1, odd, odd, and 1, 1 is even, or they are equivalent. So we can either say A is equals A prime, B prime, or AB, or we can use again the special symbol A exclusive NOR B. And the symbol is, we just put a bubble in front of it. Okay, so this is our expressions for odd and even functions. You can find the truth tables over here as well, and their expression. These are also important, which we are going to use them a lot. And exclusive OR functions, they can also be implemented as a 3-input ones. Again, if it is XOR, that means odd number of ones, 1. So there is 1, so 1, 1, so 1. As we have got 2 over here, it's even, so it's 0. 1, 0, 1, again, it's even. 1, 1, 0, it's even. And 1, 1, 1, 3 ones, that means it's odd. Okay, so either we can symbolize it like that, or we can divide it into 2 gates, 2 stages, and we can also use it like that. They are both acceptable. Okay, so that's all I want to say for this chapter. If you have any questions, write them down and feel free to ask them during the office hours or during the live lectures. Thank you.